Today we have the privilege to have Shakhar Smorodinsky from Ben-Gurion University, and he will tell us about geometric versions of Zarankiewicz's book.
Thank you, Ross. It's a great pleasure to be here. I will try to entertain you about some problem in extremal combinatorics, and before I get to more of the details. And this is based on joint work with חיה קלר. אם אתה נוגע, אתה הורס את זה, זוכר? הנה, ידעתי. אסור לגוע. אתה עושה עם המדלת הזה, ימין השמאל. רגע, למה? אבל אני אוציא לי יותר.
זה אולי לעבור של הפרויקט.
הוא מעברת על ה... הנה, זה בסדר?
The question will check. Did you want to hear?
Yes, so this is a joint work with חיה קלר, and it's about a problem in extremal graph theory, which is part of extremal combinatorics. Why do we hide the title?
And if you're changing slides, it is not. The slides have not changed on the Zoom. You're aware of that?
No.
לא, אני לא חושב על הצ'אט הזה, נעלם אחרי כמה שניות.
הנה, חייב וידאו פאנל.
בדיוק.
וידאו.
עד לך עכשיו? לא, אני אמציא אחרי זה עכשיו. ראיתי, לא היילייט את הלאדם. עם הקיפוד. Yes. Okay, so what is extremal combinatorics? So philosophically, one can think of this question and how complex can a system be without avoiding nice pattern, nice configuration? Or if a system does not contain a nice configuration, maybe you can say something to bound the size of something. And graph is one typical creature, and let me just mention in the realm of the combinatorics, we have Ramsey's theorem, which tells us that no matter nice example.
Sorry to interrupt, but on the Zoom we can only see the title page of the talk.
Gather 18 of these young children to your BSc program. There will always be a four tuple of them, such that either they pairwise know each other from before, or pairwise do not know each other from before. And in the language of graph theoretic language, this means that if you look at the complete graph on 18 vertices and you color the edges with two colors, red and blue, then either you have four tuple, all of which pairs are red, or all of which pairs are blue. It's homogeneous.
There's a problem in the Zoom. They only see your first slide.
I only see my first slide. So the question is who gets the privilege?
You touch it. You touch it.
Stop the slide again.
Maybe when you stop the share and start the share, we have a problem too. Maybe you share the wrong. Maybe you share the wrong. Now it's okay.
That's better.
Move it.
Okay. Yeah. Okay. Yeah. So I'll give you a few examples. They actually more or less they are in the realm of what is called Ramsey theory. Van der Waarden's theorem tells us, for example, that no matter how you partition the first n integers into two sets, for example, if n is large enough, one of the sets will have a 3-term arithmetic progression. Or if n is even larger, k-term arithmetic progression for larger k. So, and in the language of coloring, this means that no matter, so for any fixed k, there is n large enough that if you k color the first n integers, there will be a k-term arithmetic progression. All of those elements are of the same color, a monochromatic long arithmetic progression. This is one. Hales duet is even a generalization of that theorem to what is called into higher dimension. So you can think of I will not get into the details, but if you take the grid, some grid of k by k by k to some power d, and if d is large enough, then no matter how you color the elements of the grid, there will be a combinatorial line. And let me not define what it is, but it's the analog of arithmetic progression in higher dimension. So all of which elements of the line are of the same color. And I want to, and there are many examples of very nice theorems in extremal combinatorics, like the sunflower lemma, etc. And I want to focus about Turan's type theorem. So let's focus on that. So what is Turan's theorem? Turan's theorem tells us the following. So if you denote by KR the complete graph, so shall I define what a graph is? So the complete graph on R vertices, so every pair of the R elements are neighbors, then if you have a graph on n vertices that does not contain some clique of size R plus 1, then the density, the number of edges is bounded by this number. And as you can see, this number is, so n squared over 2 is roughly the size, order of magnitude of the complete graph. The complete graph has n times n minus 1 over 2 edges, and the density of such a graph that does not contain a clique on R plus 1 vertices is at most 1 minus 1 over R plus something that tends to 0. And this is tight, so you cannot improve this bound asymptotically. And as is given by this example of Turan graphs, so Turan graphs, and in fact, those are the only extremal configuration. Those are the graphs that maximize the number of edges without containing a clique of size R plus 1. So roughly what you do is you partition n elements into n over R sets, and such that the difference, well, if n does not divide by R, then you just make sure that the difference between any two groups is at most 1. And you, so these are the R groups, and every two vertices that belong to different groups are connected by an edge. So of course, this does not contain a clique on R plus 1. And if you calculate, you can calculate how many edges you have, just roughly every pair of parts have n squared over R squared. Edges times R, choose 2 pairs. This is what you get. It's the same asymptotics. And there is even a better theorem, so to speak, a generalization of that by Erdős and Stone, that tells us that in fact what matters is only the chromatic number. So you can ask the question about general graphs, not necessarily clique on size R plus 1, but some h, so you can define this extremal function. How many edges can a graph on n vertices have if it does not contain a fixed graph h as a subgraph? Not induced, just contain. And what Erdős and Stone told us is that it only matters what is the chromatic number. So just to remind you, the chromatic number of a graph is the minimum number of colors needed in order to color the vertices, such that two adjacent vertices get different color. And as you can see, this generalizes the previous bound of Turan, because the clique on R plus 1 vertices has chromatic number, of course, R plus 1. So it's written here 1 over R. But it's more general. But as you can see, it does not tell us. It's also true for when the chromatic number is 2. But when the chromatic number is 2 of h, so basically this is called bipartite graphs. It tells us that this is some little O of 1 times the number n squared. So still, so all we know is that it is really, I mean, the density is really much asymptotically much less than n squared. But what is it exactly? This does not tell us what's going on there. And so this is the only left case. And this became known as the Zarankiewicz problem.
So the correct order.
The correct order of magnitude is, this is the question. In fact, what Zarankiewicz asks is, well, it's enough, so to speak, to bound what happens if H is a fixed graph, but a complete bipartite graph on T and T. So T now is the constant. And so how many edges can a graph have without having T vertices and T vertices and any pair of edges between them?
It's a Ramsey question.
It's not a Ramsey. It's a Turan question. Ramsey question tells you that either or either. So when no matter how you color, you get something.
It's a Ramsey question on different graph.
No, it's not a Ramsey question. It's just bounding the maximum number of edges. Ramsey tells you that no matter how you color, one of the color will have something.
Okay.
Here you just it's a Turan question. It's and in fact it's a
The question for a complete bipartite graph implies the answer.
Yeah, of course, the question for a complete bipartite graph implies something about any bipartite graph of the same order, but it does not imply, I mean, what, for example, if the complete, we will mention, like if it's an even cycle, it's another famous question of Erdős about the extremal number. This is also not known. So there are many interesting problems here that are not known. And what I wrote here is cheating a little bit because I'm saying, let's talk about the maximum number of edges in a bipartite graph on n vertices that does not contain.
The graph itself has to be.
The host graph, the graph on the n vertices, it's enough to assume that this is bipartite.
When you say it is enough, it means bounds on both directions that are tight.
Yes, bound, if I know a bound or asymptotic bound on that function, even assuming that the host graph is bipartite, I will also know the answer almost for the original graph. Why? For the more general question that the hosting graph is not necessarily bipartite, but why? Can you see why? Why is it enough to assume that? Why is it enough to only talk about bipartite graphs on n vertices? The reason is that every graph contains a bipartite graph on half of its edges. So if the graph has n edges, it always has a cut, a bipartite graph on half of the edges. And the easiest way to see it is just randomly partition the vertices into red and blue. So each vertex gets with probability half blue or red. What is the probability that edge is really between the colors and not inside the color? What is the probability that you earn the edge? It's 1/2, right? Quarter times quarter, right? It's 1/2. So the expected number of edges,
Specifically,
there will be
for a specific edge?
For a given graph. You fix a graph and now you randomly partition into red and blue. The expected number of cut edges that will go between the sides will be at least half of exactly half of the edges. So there is a partition that gets you the half of the edges. If half of the edges is bounded, if m over 2 is bounded by something, then m is bounded by 2 times that. And we are interested, I mean, the problem is difficult enough that we are interested not in the exact constant, but in the asymptotic. So everything here will be, in this talk, I will try to throw away to the garbage all the details. I'm detail blind. I cannot see all these constants. We will have enough even without that. Okay, so you can say, okay, what is T and why T and T? Why not S and T? Why do I assume that the bipartite? Because this is the general case. It's general enough. If it's not balanced, if it's not T T, it's also, I mean, there's a whole industry about that. If it's very unbalanced, there are some results that are better than what we know and so on. But this is the interesting point. So from now on, we are talking about bipartite graphs that do not contain some two sets that.
This formulation is due to Zarankiewicz, the bipartite KTT3.
I don't remember exactly the history. This type of thing, I'm not sure that it doesn't matter. It doesn't matter.
But
Okay.
in literature, they're considering this formulation.
I don't even remember. So I have to open Wikipedia again, but I'm not sure that Wikipedia knows. So it's, who knows what has been done? But I'm sure that he didn't. Everybody noticed that it doesn't matter if it's bipartite. Okay, so here is the code.
Like an analog to replacing KR by KTT.
Exactly, it's the analog. You're talking about the
KR.
You're talking about the
You
hosting
take
graph?
the host and the guest, both of them you replace by.
Yes.
By complete bipartite and symmetry.
So the first theorem that tells us something interesting about the order of magnitude is this very famous theorem of Kovary-Shoshin 2, and that tells us that it's really little open square, and the bound is something like, again, you see, I write big O because it's a constant, absolute constant depending only on T. I should have written OT. And we are only interested about the n, the asymptotic of n, the number of vertices of the hosting graph, and it's slightly less than 2, then n squared, it's n to the 2 minus 1 over t. Remember,
This is up.
for example, when it's a K2, when it's 2 vertices and every pair here is connected, and you don't have this configuration, it means that the graph has at most n to the 3 half edges. Order.
But this is just upper bound.
Just an upper bound.
Just
So it's only known to be asymptotically tight for 2 and 3. I will not have time to get. I could tell you about the construction. Maybe just hand wave you might have heard. The construction for the case 2. So to construct, it's not a trivial construction. To construct a bipartite graph that has many edges, and vertices here, and vertices here, and square root n edges between them, still you will not have a cycle of length 4. A 4 cycle and a K2, notice it's the same. A 4 cycle, right? I mean, I could write a K2 like that. I could draw it. So this is one side and this is the other side, right? So it's a 4 cycle, right? K2 is the same as C4. If you don't have this configuration, head into the 3 half edges, and you want to construct something like that, and the construction comes from the incidence between lines and points in a projective plane. So basically, what you do, you take a prime, for example, that is roughly square root n, p, and look at this ZP square, so the projective plane, and take all the lines. You have p square lines, p square points, so n and n. And look at all the incidences between line and point. You see every line passes through p points, which is square root n. So you have n to the 3 half such edges. And of course, you don't have a K2 because there is only one line through 2 points. Okay? And the 3-dimensional is also, you say, take some incidence construction between points and spheres. Okay, but let's not get into that. So, so this is the big open problem of Zarankiewicz, improve the bound for t equal t is 4. Let me give you, because it's a colloquium token, not a combinatorics, so let me give you a sketch. It's a very simple proof, in fact. This upper bound. Let me give you a sketch of the proof of that. Okay. So what? It's double counting. Simple double. What do we count? We are given a graph, 2 sides. Let's call it the blue side, the red side. And what we count is this star, the one K1T. So we will count. So we will have something like a graph here, and we will count how many. So we have T guys here that are connected to one guy here. It's a star, the center is here, that we will count them from perspectives. The first perspective is from the center of the star. Okay. So how many do we have? Well, assuming that all degrees is at least t, if you have n vertices, call them 1 to n here, and the degree, the number of neighbors of the vertex I, let's call it di. How many stars are centered at this vertex? Di choose t. Okay. So the number of stars is the sum of the degrees on the left side choose t. On the other hand, I'm saying that trivially it is bounded by t minus 1 times n choose t. Why? Because if we count it from this perspective, I fix some t tuple, and I ask myself, how many stars are such that these are the t leaves? How many? Well, the center is somewhere here. There is one center, another center maybe. How many? At most t minus 1 center. Because if there would be t centers that use the same t leaves, we will have a ktt, right? Okay, so each t tuple can be the leaves of at most t minus 1 stars. How many t tuples are there? At most, n choose t, most. So it's at most t minus 1 n choose t, and t minus 1 n choose t asymptotically is roughly n to the t, n to the power t. So this is one. What about the other side? I want to make
the assumption about the eyes.
nothing.
No assumption.
Nothing. You will start nagging me about what happens if the degree is less than t now. Hmm?
So DI, you really want to increase them as possible. This is the idea. So
What are you? You are saying
this
this does not hold. That's what you are saying.
He's trying to guess an aspect.
My next step is using Helder's inequality. So my next step is first of all not blind you with details and saying that this order of. Well, I thought you are bothered by the fact that what happens if the degree is less than t. Throw these vertices away.
Yeah.
You will throw at most n times t. So now assume that all vertices on the left side have degree at least t. Okay. So we will have to add n times t, but this is much smaller than.
But then you have to throw it also from the right.
Right is
Right is always true. Still true. I only throw vertices from the left hand side. If it's a monotone property, if you don't have a KTT, also a subgraph. Do you agree that I can say that this is some constant times di to the t? That's okay? Okay. Only this one, if t was 2, you would say let's use Cauchy-Schwarz inequality.
unless di are small,
But t
except for small di's.
yeah, we don't have small di's. All the di's are at least t. So here I just use Helder's inequality. This is a nice exercise to show that, right, the sum of the tth moment is at least the sum of the numbers to the t, but you have to divide by n to the t minus 1. Because the vector, if you look at the scalar product, if you look at the Helder inequality that I use here is that the 1 times this vector d, right, is bounded by the sum of 1 to the power 1 minus 1 over t or something like that times di to the t, right? To the yes, sorry, I write it. So this is no. I write this. So this is bounded by the sign of the 1s to 1 minus 1 over t times the sum of the di to the 1 over t or something like that, right? Right, so the sum, whatever did I write? Did I mean, did I change the, forget about it. You do the math. Anyhow,
So Helder inequality is Cauchy-Schwarz.
Cauchy-Schwarz in our dimension. This is why we get to the t minus 1.
For P norm.
Yeah. So you just think of the sum of the di as the sum of the di times 1, all of this to the power t, the sum of the di to the 1 over t to the power t, and so on. This is okay. So what is the sum of di? The sum of the degrees, it's the first thing you teach in graph theory. The sum of the degrees in a graph, simple graph, is twice.
Only look at one side.
Hmm?
Only look at the left side.
The sum of the di.
The ideas are only on one side.
What do you mean on one
So it
side?
will be only
But the
one-
two,
one E.
Hmm?
you do not need the two because it's
Yeah, the two.
because
This is 2 times, so the sum of the
you don't
di.
need the two because by part of graph, if you sum the degrees on one side,
One side.
the number of edges.
Yeah, you're right, actually.
So
You're
this
right.
is not,
This is the typo.
This is second.
Because
This is second lesson in second in the.
Yeah, no, it's also not, it's wrong here. I should not have written 2.
But you already said
Because,
all constants are one.
But actually, this proof is proof for general graph. I do not need to assume that the graph is bipartite, but never mind. So this is for the bipartite. I only summed on the left hand side. You're right. I shouldn't have taken. So this is exactly the number of edges, and to the power t over into the t minus 1. So that's it. So we basically what we get is roughly that the number of edges to the power t is this number, which is some constant depending on t, and then we just get this one. That's it. Okay. Yeah, questions? No. So this is what we know, sort of the state of the art for the general case. And I promised to talk about incidence geometry. So now we will talk about all kinds of bipartite graphs that arise as incidence in geometry. As I mentioned, incidence in the finite projective plane. We take real geometry. We take, let's say, n lines in the plane and n points in the plane, and we count the number of incidences between them. So it's a bipartite graph. Points on one side, lines one side, and I say that the point is connected to a line if it lies on the line, if the line passes through the point. Okay? And this was a famous question of Erdős from the, I think, the 40s. But how many incidences can you have between n points and n lines? He asked more general m points and n lines, but doesn't matter. N points and n lines. And he noticed that this graph does not have a K22. Therefore, by this general graph theoretic bound of n to the 2 minus 1, now t equals 2. We get n to the 3/2, and he provided a lower bound, just using the grid, of n lines and n points that achieve at least n to the 4/3 incidences. And he asked what is the real asymptotic. And that was left quite some time open until Semered and Trotter proved in 83 that this bound is roughly n to the 4/3. This paper that they wrote is, I could, even though I did not try to read it, I could say as a gossip that is unreadable. I know people who tried to read it. So it was not something you would teach in a course, in a graduate course, undergraduate course. But then later on in 90-something, it was 98. Somebody Hungarian commission came and gave a very beautiful, almost one-line proof of that. Using the topology, using the Jordan probability, this planarity of graph and so on. Something called the crossing lemma, I don't want to get. So this was sort of the cornerstone of incidence geometry, this result. And it quoted many times, and it's also, I mean, this incidence geometry is a big business. It has to do with it has many applications in computer science and algebra. There is a question once I heard about how many equal minors you can have in what is called totally positive matrices, and it has to do with incidences. I have a paper about that as well. If you use higher dimensionals, you get some incidence. Okay, so this is tight descent to the 4/3. Game over. But we have an unsolved problem from the 40s, and maybe it's one of the most famous open problems in discrete mathematics, definitely in discrete geometry. And this is the following simple-minded problem. How many, among n points in the plane, at most, how many pairs of points could be a distance exactly 1? Okay, this is famous unit distance. So you can define this function, right? You're given a fixed set P of n points, you look at how many pairs are at distance 1, among the n choose 2 pairs, and you want to maximize that. So how big this function U of n could be. And another famous problem about unit distances is the Hadwiger-Nelson problem you might have heard, which is the chromatic number of the plane. By compactness, you can assume that there is a finite number of points, how many colors you need in order to color them, such that the unit distance graph is not monochromatic. It is known to be at most 7. The lower bound was 4. Now it's 5 by a result, and nobody knows the answer, whether it's 5, 6, or 7. But we are talking about the density of that graph.
person who proved that it's 5 is a biologist.
A famous biologist, an amateur.
In 30
Brede
years,
Gray.
will live up to 200 years. This is not a claim.
Yeah.
It's a person.
או בריידה גריי.
הוא אמר שאנשים יחיו 200 שנה, 30 עד 50 שנה.
So this problem, Erdős posed this problem in 1946, and it is still open. Nobody knows the asymptotics of the function, and the gap between the upper and lower bound is very big. So this is a big problem, and you can think about it. And if you improve something, so if you obtain sharp asymptotic bound, it's worth doing that, because then you will get a lot of money from Erdős. Erdős posed $500. This is a nice problem you can give to high school students, because it's tempting to think about. But there is two things you have to, if you're fair with them, you have to be careful, at least warn them. One thing is that if you only look at the combinatorics of the plane, it's not enough. Because if you change the norm, almost all other norms, what the best known upper bound today is also that is known, we'll see in a second, is also the lower bound. Okay, just that this Euclidean norm we are stuck with. So if you change it to some non-convex, non-smooth norm or something like that, you can have so what we know about this word record now. So Erdős noticed that it is at least this number. It has to do with this basic thing in number theory, that how many times you can describe a number as a sum of squares. Okay, that if you know that, you can see why we have this. So you take the grid and you look at you choose carefully the grid, you look at the number, you put a circle around every point, and you look at how many other. Yeah, so that's what we notice. As you can see, this function is not only that it is superlinear, it's much better than n times some polylog. So it's much better than a lower bound of n times a log n to the power of 12. Okay, because the extra factor, we have something like 2 to the log n of log n, and 2 to the log n of log n is much more than 2 to the 70 times log n, which is power. Why do I say that? Because an easy lower bound comes from the cube, or we just take, n log n is an easy lower bound. If you start with something that has some number of edges, you just move it one unit apart. So you take a copy of that, you move it 1 unit apart, so you remain, it's a rigid motion, you remain all the guys here, all the unit distance, but each guy now has a twin that is a unit distance apart, right? So if I would write it as a formula, I want to make 2n copies, 2n vertices, and I know how that I have at least f of n. So it's like saying that it's 2f of n plus n. right? This function is n log n. This is a lower bound. It's a lower bound in any number. Basically, it's the cube. Take the d-dimensional cube that has n log n. And the best currently known upper bound due to Spencer's total is n to the fourth root. Surprise, surprise. And as I said, if you change the norm, you can construct a matching lower bound. But for the real Euclidean norm, we don't know.
What was the previous result of Smorodinsky? Rotter we say.
Smorodinsky Rotter for the line was the same bound, n to the fourth root. Okay, now the question that you should ask me, why the hell do I bifurcated and started talking about this unit distance problem, because I promised to talk about incidence geometry. But before that, let me just mention that this unit distance graph, so think of the endpoints as vertices and connect to if they are an edge, if they connect to an edge if they are a distance one apart. That graph does not have a K23 as a subgraph, right? I cannot have 2 blue points and 3 red points and all the distance blue, red are 1, because if I would have something like that, it would mean that take the first blue point. If you have 3 guys at distance 1, it means that the circle centered at this blue point of radius 1 passes through the 3 red guys. But 3 points determine at most 1 circle, not to speak about 1 unit circle, right? So there is no other circle that passes through it. So there cannot be another point of distance 1 from this. So if this graph does not contain this structure as a subgraph, I'm saying n to the 3/2 is an upper bound. So I didn't tell you that the unbalanced case, if it's not KTT, but KST, and S is the smaller one, you can plug in the 2 minus 1 over something, you can plug in the good one, the one that will make it smaller. Yes, the same property. So if S is smaller, 2 minus 1 over S is also smaller. The upper bound is better. So it's 2 minus 1 over 2. So it's n to the 3/2. That was the observation, again, of Erdős from the 40s. But how does it have to do, what is the relation to incident geometry? So the observation is very simple, that if you fix endpoints, that set that you want to bound the number of pairs at distance 1, what you can do is look at the set C of circles as follows. Put a unit circle centered around about each of the points. So we have blue, we have 4 blue points. We will draw 4 unit circles, 1 for each point. So 1 centered at this point, 1 centered at that point, 1 centered here, and 1 centered at this point. So we'll have something like that. And the observation is that the number of incidences between these n points and the n circles that I just draw, unit circles, is exactly twice the number of unit distances. Because every time I had a unit distance, I had a circle. If I had a unit distance, I had a circle centered at, let's say this is these 2 guys at a distance 1. So the circle centered around this point is incident to this point. This is 1 incidence, and the other way around this one. So it contributes exactly 2 incidences. It's significant. So the number of unit distance is twice the number of incidences. The real question is how many incidents? So this is still open.
It's not lines.
It's circles. It's circles. And it's open even when the circles have arbitrary radii. There's another question. So you can see how incident geometry started developing. So let me tell you about a relatively recent result, not so recent, but in the last 10 years, that had a far-reaching generalization of this n to the 4/3 bound. And this is due to Jacob Fox, Janusz Pach, Adam Scheffer, Andrew Suk, and Joshua Zal. And what they defined is some bipartite graphs that are semi-algebraic. And I will tell you what I mean by that. So I will tell you. So in words, it would be, suppose you can describe incidences by thinking of the one side as points in some Euclidean space, another vertex on the other side is another point, two sets of points in Euclidean space. And you draw an edge if you can describe this relation by some semi-algebraic relation, in the sense that if you think of the 2 points as 2D variables, 2D coordinates, D and D, then and you have some constant number of polynomials in mind before you start. And this guy satisfies some semi-algebraic relation with this polynomial. Inequalities. Inequality. So even a Boolean combination of fixed number of variables. So let me just say, so it's a bit more formal. So this is, I noticed just before the talk that this is bigger. So you fix some R. So first of all, we will say this. So I want to say that I fix an R is constant. And then I want to talk about semi-algebraic with this constant complexity description, which is R. So I have just in all of the examples I gave until now, there was one polynomial involved. Like you can talk about a point in a circle, like a point lying on a circle of the one as the distance being one, some two-variate polynomial of degree 2 equality. It's algebraic even. And you will see there is a big difference. But I want to talk about semi-algebraic.
And these fix this question?
So no, this is not. So that the only thing in the exponent is going to depend on the dimension. So let me describe. So we have R, think of R as being 1. Okay, because it doesn't matter. So we have a Boolean function, a Boolean formula, you have this polynomial of degree R. And now I say, what does it mean that a graph is semi-algebraic with complexity R? R is 1 for them. Understand? So we have, so it means that so in dimension D, it's all in dimension D. So but this is going to be the only thing that actually is important. So you have two sets of points in RD, and between and I will draw an edge. So these were going to be the two sides of the graph, two sets of vertices. I will think of them, and I will say that the edges are all the x and y, all the x comma y in P times Q, such that this formula is satisfied. So basically, it satisfies some semi-algebraic, right? Let's say if it would be real algebraic, then the polynomial is 0 on that two, like we have in circles. Okay. So this is a semi-algebraic graph of description complexity. Let's call it R in dimension D, which I mean, right? What is the result? The result says that if the graph is KTT3, then for any fixed t, then the number of edges is n to the 4/3 in dimension 2. So now we are talking about the 4-variate, like 4-variate polynomials. And of course, the constant here in the big O depends on t naught, but this is the exponent for 2 dimensions. And for d dimension, it's this bound. So you see, it does not depend on the t. It's only the constant. It does not depend on the KTT. And we get 2 minus 2 times 2 over d plus 1 plus epsilon. So it's actually the technique involving the proof is such that you can, for any epsilon, you can increase the constant here and get this bound. So you can get arbitrarily small, but by paying for the constant. So focus on this for a second. The n to the 4th, so 2 minus 2 over d plus 1 roughly. So this is the get here. And one ingredient, a big ingredient in the proof of this theorem is the following. Completely combinatorial characterization or bound without using algebra or geometry. Just some combinatorial that has to do with what is called Vapnik-Chervonenkis dimension of a hypergramh.
So just a second. In the previous slide, if you don't assume it is algebraic, then you have only the 2 minus 1 over t.
Yes. But if I require much less, I just want to talk about some combinatorial, another combinatorial property, we'll see that I can get something better. So what they proved is the following, that if a graph has so-called, it's KTT free, but it also has what is called bounded VC dimension, and I will explain. So this is some combinatorial property. I will explain what it is. Then even if you take T very large, then only the dimension matters. So the bound becomes n to the 2 minus 1 over d, even if T is much bigger. But the big thing is, what exactly do I mean by the VC dimension of the graph? Okay. You have to contrast it with the Covariant theorem. So there you get 2 minus 1 over d, which is much bigger than 2 minus 1 over d, when t is much bigger, greater than d. So you can think of t being 2 to the d. Okay. So, and more generally, that I shouldn't have brought. This is more generally for unbalanced n vertices and n vertices. It doesn't really matter. Let's not confuse. Let me give you a crash course on VC dimension if you never heard what it is. It's a combinatorial property of hypergraphs. Okay? So a hypergraph is a set of vertices. It's a generalization of a graph. It's a set system. You have some, in our case, it doesn't matter if it's finite set V, we call it vertices. But E now is not necessarily subset of size 2, but arbitrarily size subset. We call them hyperedges.
Not fixed. Size is not fixed.
The size is not fixed.
Sorry, what does VC stand for?
VC for Vapnik and Chervonenkis, two mathematicians. Chervonenkis. VC dimension. What is the VC dimension of a hypergraph? First, a VC dimension of a hypergraph is the following. First, we need to define what is a shattered set. So, given a hypergraph, a set S of vertices, not necessarily hyperedge, any set, it's called shattered if you look at the intersection of all hyperedges with the set, if you look at all the patterns, you get all possible patterns, all 2 to the S possible subsets. Then we call it shattered. And the dimension of the hypergraph is the maximum size of a shattered subset. Let me give you a quick example. Suppose the hypergraph is a very simple-minded. I just have think of it as number 1 to up to n points on the reals. N reals. And it doesn't matter if it's real, just order set. And let's just look about all subsets that are consecutive. All subsets, in other words, that you can cut off by an interval, some interval. Okay, this is the hypergraph. It has 1 and 2, 2 and 3, 3 and 4, or 1, 2, 3, and so on. All possible discrete intervals. What is the VC dimension of such a hypergraph? What is the largest shattered subset? Well, it's 2. You can shatter 2, but you cannot shatter 3. You cannot shatter 3. You cannot, if you have 3 points, you cannot have something containing the first and the last one without containing the middle. Right? So the VC dimension is 2. By the way, if I will take a non-trivial example, I will take points in d-dimensional Euclidean space. This is the 1-dimensional. And I will look at all subsets that I can cut off with a half space. So everything above some linear polynomial or below. If you know Radon's theorem, you know that the VC dimension is at most d plus 1. You cannot have d plus 2 shattered. Why? Because Radon's theorem tells us that in d dimension, if you take d plus 2 points, you can always have a non-trivial partition like that, whose convex hull intersect. So if you have a non-trivial partition whose convex hull intersect, there any half space which fully contains one of the guys cannot leave the other set outside. It will also contain a point. So the VC dimension is d plus 1. D plus 1 is the simplest. You can get every set. So these hypergraphs, which are highly non-trivial, but they have a bounded VC dimension. So for example, if we talk about incidence between points in half space without KTT, you automatically get something. So, okay, this is a VC dimension of a hypergraph, but what the hell does it have to do with a graph? I talked about a VC dimension of graph. What do I mean by that? So what I mean by that is very simple. I look at the neighborhoods. So a bipartite graph, it's a way to look at on a hypergraph. So what do I mean by that? So suppose if I have a bipartite graph, I can think of a hypergraph where A is the set of vertices and B is the set of hyperedges. It defines subsets of A. How does it define? Every vertex in B, I look at all its neighbors in A, that's a subset, and that's my set system. And if that set system has, and then I can talk about also the other side. And if that set system has VC dimension D, then I say that the graph has VC dimension D. So this is what written there. Yes, the neighborhood hypergraph. So questions about?
So
now
you pick a side.
I don't have to. I can talk about both. So I take the largest among the two of them.
So just to feel, what are two bipartite graph with VC dimension of most 3?
Say it again.
What to feel what is the information? What are the
graph.
bipartite graph with VC dimension 2, 3?
So the incidence between points and lines, for example, such bipartite graph have VC dimension 2, right?
Yeah. So what can you say in other words? The properties can you?
So that's what I want to say, that if, so I recall that this theorem tells you that if the bipartite graph has VC dimension, it's KTT free, but the VC dimension is D, then it has n to the 2 minus 1 over the edges. We don't know what exactly is the asymptotic. It was recently improved for the balance case to little o without an explicit exponent using the semi-ready regularity lemma to little o. We don't know, but you might say that I'm lying. What you give yourself discounts that you say that the VC dimension is bounded and you want us to talk about Zarankiewicz, which is math. It's not such a big discount. I want to tell you, I don't have time to talk about it. I just noticed that a few weeks ago, before I gave a talk in Jerusalem, that in fact, if you only assume that the graph does not have KTT as a subgraph, then such a graph has VC dimension which is bounded by T plus log T. It's not much, it cannot be, so if the VC dimension is bounded, you get something. If you don't care about the VC dimension, you only care about the fact that it is KTT free, it's still the VC dimension cannot be that big. It's still T plus log at most. And that's easily seen by saying, suppose you would have T plus log T, let's say log T here and T here. Suppose you have T plus log T vertices that you can shatter. What does it mean? These are the edges, every subset here, every point here, you look at the neighbors, this is a subset. So let's look at if I can shatter this set, this is a contradiction. Why? Because let's look at all subsets. How many subsets do we have that fully contains T among T plus log, these T guys? How many subsets that do you have that contains the T tuple in a set of size T plus log T? The answer is as much as the subset of these guys, the union of every subset here and here. You have 2 to the log T, which is T. Each such subset is realized somehow by a vertex here that is connected to everything plus this whatever. So you will have T such guys that are all connected to this guy, you will have a KTT, right? So, okay. Ooh, I have to continue. So, I told you that n to the 4th third or n to the d something minus is an upper bound if the VC dimension is small, and we have the result of Fox-et-al that tells us if things are semi-algebraic, you get n to the 4th thirds or something like that. But these guys, including Terry Tao, they noticed that if you talk about, let's say, incidence graph of endpoints, so now it's really semi-algebraic. It's not x. So think of axis parallel rectangles in the plane, not the boundary, the full dimensional rectangle. So now it's about containing. So you have points and rectangles, and a point, if a point is inside the rectangle, it's an edge. And that graph does not have a KTT. It's got an almost linear bound. They show that it is, let's say in the plane, they got n times log to the 4n, much better than what we get from previous results. And for d equals 2, it was improved to n log n in 21. And this started, caused Sariel Arpel and Timothy Chen to systematically study where can we get almost linear bounds. And this is what, for example, they were able to prove. So these are really semi-algebraic. So you have points on one side and some full dimensional sets on the other side, like axial parallel boxes or pseudo-discrete plane, which is not even algebraic. And they got this bound, let's say, in log n. So for example, look at this result. This result about pseudodisks. What are pseudodisks? Pseudodisks is a collection of n simple Jordan regions in the plane, such that the boundary of any two of them intersect at most twice. Simple full dimensional Jordan regions, such that so it's not even algebraic, it's just topological. So you have something like that, right? Okay, it's a family, and so on. By the way, it's a special a homotets of a fixed convex body is a special case of such a family. Okay. So they were able to prove n log n. And 5 minutes. So let me try to convince you that we can do a completely different approach. I didn't tell about the previous approach to Zarankiewicz and get a linear bound, for example, on a even more general problem of points. And so to this linear bound, not even, but for a more general problem of bounding the incidence between not pseudo-discrete points, but two families of pseudo-disks. You can think of a set of points as a special case of a set of
Exist parallel boxes, what you get.
We generalize this to axis parallels and axis parallels. So two families of axis parallels, not axis parallels and points. But more important is the approach. I want to tell you something about the approach, and then I have to give a crash course on what is epsilon net in hypergraph. So epsilon net in hypergraph is simply a heating set. So a subset of the vertices that stab all the hyperedges, but only the heavy hyperedges, those that are epsilon heavy. So those that contain an epsilon fraction of the point. So a subset T is called the heating set if it intersects like this. Every edge and an epsilon net is a subset that hits only, we care about only the heavy hyperedges, those that are epsilon heavy. Okay, this is a very famous notion in hypergraph theory. And why do we care? First of all, it does not always exist, a small size epsilon n, because if you have this complete hypergraph on epsilon n vertices, so n vertices, and every set of size epsilon n is there, you cannot have something that is of size depending only on epsilon. I mean, you will have to have at least 1 minus epsilon times n. You cannot leave out epsilon n vertices because that would be a hyperedge not. What is the connection between epsilon n and VC dimension? This is a famous theorem that says that there is always an epsilon at a heating set for the large hyperedges that depends only on epsilon. So for example, if you only want to hit all edges of size square root n, you can do it with roughly square root n log n vertices. Or all those containing n over 2, you can do with a constant, an epsilon constant. It's quite surprising. But if the VC dimension, and this is asymptotically tight, and we want it
too big. Well, where is the VC dimension here?
here, in this bound. It's linear. It's d over epsilon log 1 over 2. This bound. The side of the heating set depends on d and epsilon. And epsilon could be any number between 1 to, between 1 over n to.
D is the
D is the VC dimension.
Okay.
But we ask ourselves what we define the notion of epsilon t nets, and now I want to hit with sets and not with vertices. So I want a whole set. I want a collection of t tuples as small as possible, such that every large hyperedge is completely contained one of our guys. Like here is an epsilon 3 net. Okay.
So t equals 1 is
T equals 1 is it's an extension. For t equals 1, it's exactly this epsilon. And what is the theorem that we were able to prove? This is a different paper with Nogalon and Bruno Jortou and Yelena Ejitsky, my previous postdocs and students, and with Chaya. That it's the same almost. So there is always an epsilon t net that depends on the only like that on the an epsilon. And well, I hid the constant t in the big O. T is in the big O. But t is, since t is constant, I should have written O. Why does this relate so we were able to prove even a better bound of 1 over epsilon for the special case of this intersection graph of two families. So two families of pseudodis. They define a hypergraph like before. Every vertex look at the neighbors. This is the hyperedge and so on. And then we have an epsilon t net of size.
What is the role of the two? Why two families?
It's a now it's a bipartite graph. We have a red family of pseudodisc and a blue family of pseudodisc, and I look at the intersection of a blue red. And I assume that there is no.
So if there is intersection, there is an edge.
It's an edge, but I assume the graph does not have a KTT as a fabric.
Okay.
And what we proved is the linear upper bound. I don't know if I mentioned it here. And the way we do it is the following. Let me quickly say. So let's ignore light vertices, those that have degree at most epsilon. Well, I will tell you what epsilon in a second, but those that have degree less than epsilon n, I will ignore them. They can contribute at most epsilon n square edges. The heavy hyperedges, those that contain many, so those, look at the B side, those that have degree at least epsilon n. First, I will take an epsilon t net, a small number of t tuples, such that every heavy vertex in the neighborhood there will be a t tuple containing it. So it will be connected to all the t lines. So, but how many such heavy vertices you can have? Well, at most 1 over epsilon, according to the number of t nets, but each such t tuple can be contained in at most t minus 1 vertices, otherwise you'll have a KTT. So the total number of edges that we can get from here is this, without saying what epsilon is this. If you plug in epsilon being square root n, you immediately get the n to the 3/2, which is without depending on t. Okay, but in fact, we can recurse and not immediately talk about, so I mean, throw away the light degree and look at the heavy degree. Heavy degree have at most 1 over epsilon and 1 over epsilon on each side like this. I can do it in both sides. And now I will remain with something that I don't care about edges that connect something that has light on one side. I will remain with the heavy vertices, and I can get some recursion or induction that if I can choose epsilon here to be 1 over n, I get something that looks like n plus f of n over 2, something that solves to linear. So I overdid it. So just to summarize that what we were able to get for something that is not algebraic, like n pseudodisc versus n pseudodisc, is linear bound, and the previous bound was only known for pseudodisc and point, and it was much worse. So
show again. So what the chain so they also consider the same.
They considered only the setting of pseudodisc is one side, and the other side is not pseudodisc, is points.
Yeah.
So we generalize it.
Yeah.
To two families.
And you strengthen those.
Yes, it's that. Up to now you can fight for the dependency in T, but
so pseudodisc behave very differently for a typical graph.
yes, of course.
And boxes, you say it's.
Boxes, it's n over log log n,
Not
depending
linear.
on type. It's not linear, it was n log n over log log n. And that's type. In the plane. In higher
And
dimension.
that's type.
Yes. So all these special cases are much
It was
closer
n
to
log log n.
Hmm?
For boxes, it was n log log n.
On log n over log log n.
What? Show again. You remember?
Where was it? Oh.
Here.
So in dimension 2, you get log n over log.
log log n.
Yes. But the thing is, it's a sort of a different approach than previous approach. It gives something, but we still don't know how to use it for the more general cases. I should stop here, I guess. I should have stopped.
Okay, thank you very much. One more quick question.
Very opposite.
Hmm?
Very opposite question.
Opposite question. What?
Yeah, you are trying to see what are the values of x. But if you you're asking question in one direction. So now we know about x. What can we say about the graphs? We know asymptotics.
So give me a concrete question because I'm not sure.
Oh, if I know concrete question.
You know the number of edges and you want to know.
Yeah.
If what you're saying is that if the number of edges is above something, you will have configuration.
Yeah.
You will have many.
Yeah.
But no, the extremal configurations what are.
What are the
Your
extremal
flows for the
configurations?
extremal configuration.
This is
Yeah.
this is an
Yeah.
this is a different step. Yeah, it's very difficult. It's not. What are the? We don't even know the behavior of them.
Asymptotically extreme.
Yes. And again, we don't know anything for t equals to 1. So one sort of external configuration asymptotically is the projective plane of projective sphere. In finite field, they have a whole industry of results there. It's very important. It has to do with Kakia sets and all kinds of things like that.
Thank you very much.